I will first try to explain why high pressure physics is so interesting to my point of view. So, and what's the great advantage of using NV for these measurements? So when you look to materials at high pressure, actually pressure is a fundamental thermodynamic variable. With pressure, you can tune structural, electronic, and magnetic properties of materials. And I will give you some examples. And of course, it is crucial for Earth and planetary science. And that's why high pressure physics, why high pressure technology and high pressure science actually was initiated for exploring somehow in the lab the interior of planets. So to understand also why pressure is so important parameter, we can consider the free Gibbs, the free enthalpy Gibbs, the Gibbs free enthalpy. So it's just the usual term, the free enthalpy, U minus Ts, that defines the stability of materials. Oops. Okay. Oops, it's doing strange things. I don't know why. Okay. And when I look to that, now I had the PV term, the pressure and volume dependence. If I apply a pressure of 1 million of atmospheres, which is equivalent to 100 of gigapascal, then the volume change in the material, for instance, the dependence with pressure of the lattice parameter, times the pressure will be of the order of 10 electron volts. So that's more than any binding energy, most chemical binding energy. That means that new chemistry can happen. Very different compound can happen at those pressures, and I will give you also an example of that. Pressure has also been a very efficient tool to explore superconductivity. You all know that superconductivity, but it changed a little bit the size. I don't know why, because now it's here. Okay. Maybe we have to lower it. Okay. Oops. Okay. So you all know that superconductivity was discovered by Kamerlingh Onnes at the early, in 1905, at the beginning of the 20th century. And then there was very slow increase of the critical temperatures of materials. We could reach something, and there was an important step to understand also the properties of materials was BCS theory to explain the superconductivity by the binding of electrons into Cooper pairs. And BCS theory tells you that taking into account Fermi levels, density states, there is a kind of limit around 20 Kelvin to 30 Kelvin. And that was actually what was reached, okay, up to that. So somehow all the compounds that were known for a while until 95 was something limited to 30 Kelvin for critical temperature. And then there was a real breakthrough by the discovery of superconductivity in cuprate material. And cuprate are ceramics. They are dirty materials. And Bernoz and Müller found that Labacuo was a superconductor with a great increase of the critical temperature. And that was, of course, a very surprising discovery. No one attended superconductivity, was expecting superconductivity in such dirty materials. Still, we do not understand where does this superconductivity comes from. It's called unconventional superconductivity, meaning that you don't understand anything about what's happening in that. It's not exactly true now. There have been a lot of studies. But still, after more than 40 years, almost now 40 years after, we still do not understand why the physical reason that makes those materials superconducting. And then just after that, there was a great step done by Paul Shu and his collaborator in the US, which was to apply pressure on this material. And they immediately saw that the TC rose rather significantly by applying pressure. And so they had the idea that somehow you can mimic this pressure by what they call chemical pressure. And the chemical pressure is somehow you change one compound on the one compound of the atom, and that will mimic the external pressure you apply just by internal constraint in the crystals. And so they had the idea to change lanthanum atom here by yttrium atom, which is smaller. And going to the smaller size of this system will increase the temperature remarkably above the liquid nitrogen temperature. And EBAQO is the superconducting at temperature above liquid nitrogen, and that's why we can do a lot of, for instance, demo experiments using this material very easily. It's also difficult to produce. Basically, if you have an oven, you take the different samples that you have here, and you crush them, you make a pestle, and then you cook it for a while, and you get your EBAQO sample. Paul Shu also discovered other material, and especially together with other people, he was able to achieve the highest critical temperature for a long time, which was obtained in a mercury-doped cuprate, and we will work on that. We will show you results that we have done on that, at a pressure of, and the highest critical temperature, about 165 Kelvin, was obtained at a pressure of 30 gigapascal. That's one point. And then there was another breakthrough, which is now still under strong debate, which is a new family of material. BCS theory tells you that somehow superconductivity will be far improved if you could have very light material. And then you can think of the lightest atom you can have. It's hydrogen. And following this idea, Neil Ashcroft proposed that hydrogen would be superconductor, but at pressures where first it is metallic. And metallic hydrogen was expected to occur at amazing pressure. It was predicted in the 30s by Wigner and Huntington in a pressure range, but then up to now, no one really has been able, until maybe a colleague, Paul Loubert, with whom we collaborate, was able to achieve a metallic state of hydrogen. Perhaps what he has achieved is a metallic state of molecular hydrogen. So there's a lot of still, but the pressure you need to reach that is 400 gigapascal, higher 4 millions of atmosphere. I will show you how this can be realized. And Neil Ashcroft predicted that if hydrogen is metallic, so unfortunately at those crazy pressures, it would be a superconductor following BCS theory. But then there was a second step, again, a little bit like the idea of the chemical pressure, was to now add another compound with hydrogen. And somehow, to address other samples, which are called hydride, in which somehow the structure of the crystal is very close to the one you would have with hydrogen. And those systems were expected to be also superconductor, following the calculation that was done by the prediction of Neil Ashcroft. And this is hydride is somehow the combination of a metal plus hydrogen. But to get that, you need to be at high pressure so that you have samples that have this very specific stoichiometry and structure that is specific to the onset of superconductivity. And it was found that indeed superconductivity was first found by Michael Eremets and his team in Mainz in 2015, 10 years ago, in sulfur hydride. That was indeed predicted in this material by ab initio calculation. And it was observed using resistivity measurement. And that was a very landmark paper. And the critical temperature immediately rises very significantly 200 Kelvin at a pressure of 150 gigapascal. Of course, the question is, I will discuss that at the conclusion, what can you do at such pressure? Is it an interesting material for any application at those pressures? Let's put that aside for the moment. And then there was another great step forward done by, again, Michael Remetz and also Russ Emley in the US, where they observed superconductivity in another system, embedding even more hydrogen, lanthanum hydride, LaH10. And this is somehow a structure. You see here the lanthanum atom. And around the lanthanum atom, the hydrogen atoms are organized in cage. And this leads actually to a physics close to the one that is expected for metallic hydrogen. So, and the TC is around 260 Kelvin at 200 GPa. And now, today, there has been a systematic computational exploration of binary compounds, and evidence for superconductivity has been found in approximately 10 compounds. So we would like now, again, to reproduce all these experiments at high pressure. And why do you want to do it? First, all these experiments are realized with this remarkably simple tool, the diamond anvil cell. So the diamond anvil cell consists of two diamonds with a shape, cut and shaped, with a tip. The tip has a diameter that can go to 500 micrometers to a few micrometers. For instance, people that want to achieve 400 gigapascal, they will work with a diameter of the cullet, of the tip of the anvil, we call that cullet, that will be around 20, even 10 nanometers. So you can imagine how the system will be. So the two anvils, we will squeeze them against each other. And inside, there will be a pressure transmitting medium. The material will be embedded. And then that will be used to apply hydrostatic pressure forces onto the sample itself. And there is also a lateral confinement that is ensured by a metallic gasket. So it's something that is done, for instance, in rhenium. Rhenium is the metal that has the highest stiffness. And you drill a hole in the gasket, in this metallic gasket, and this is, again, squeezed with everything inside, and at the end, you have this system. And what's remarkable is that at the end, it's like a bottle. You can imagine my bottle here. I have these two tips like that, the gasket in between, but now I can take it in my hand, and I can go to whenever I want. I could have brought it here. I could go to a synchrotron, for instance, and do X-ray measurement to identify the structure of those materials, and actually this is what has been done. So it's a very practical tool. You can even control the pressure in situ by controlling the force that is applied on the outside of one of the anvil, and for that, we have here a membrane, and we insufflate gas in the membrane. And just due to the difference of surface here to here, we control like that the pressure inside the cell. And the pressure is controlled here with this tiny capillary tube that you see here. And there's a tap here. You close the tap, and then you can have your sample at 100 gigapascal and keep it forever if you want. And there's almost no leak, of course, because if there is any leak, then everything will be removed. So this is very nice, and this has been found in the 50s, and there has been a lot of technical development on how to use the anvil. There have been remarkable discoveries found using this tool. Now, what you want to have also is diagnostics. You want to measure that your sample, after the pressure, due to the pressure that is applied on it, becomes a superconductor. So, of course, you have one approach. It's to put electrodes and measure the transport properties, the resistivity of your sample, and you should see that it drops to 0. You can imagine that you have now to put very tiny electrodes. You need 4, for instance, to avoid any bias in your resistivity measurements, and that will go onto the sample. And this is very difficult. Of course, what can also happen is contamination of the sample by the electrode, and this is very hard to reproduce. And somehow, making this electrode in this environment is a kind of art by itself. That's one property, and also you probe again the whole ensemble. You don't know, so you can have something that decreases the resistivity, but getting null resistivity is always very difficult. So this is not a very, it's an evidence for the existence of superconductivity, but you have to demonstrate something else. And what you have to demonstrate is that the specific properties of magnetic properties associated to a superconductor, which is a perfect diamagnetism. So you measure the magnetic susceptibility. And that can be done using roughly two main techniques. The first one is that you have an excitation coil, and using a pickup coil, you measure the response from the sample. But you actually measure the response from the sample and also the response of the system itself. Everything is the outside. So it's also, again, an ensemble measurement, and the sensitivity due to the dimension of the sample, which is very small. The sample will have the typical size at a pressure of 100 gigapascal of about 10 micrometer. You can be due to the constraint of the system. Basically, you are limited in sensitivity. The other approach is now to use the most sensitive magnetometer so far, that are squids material. And those squid material you want now to integrate your diamond anvil cell into a squid apparatus. The squid apparatus has a very tiny diameter, so it means that you need to make very specific diamond anvil that are non-magnetic, and that can be integrated into this system. And that's, again, very, very challenging. So with all these techniques, you do not have any spatial resolution. You probe the whole sample. You can have sample by contamination. And in the all magnetic measurement, it relies on a large background subtraction. The signal over background is typically 10⁻⁴. So you want to see a negative magnetic response over something which is a background of 10⁴. And this is very, very challenging in the data analysis. So all that led to a fierce debate on data interpretation, even questioning the existence of superconductivity. And there was work done by some theoretician, Jorge Hirsch and other two or three other people, that somehow looked very carefully to the data. And they even found that one of the main claim of high-pressure superconductivity that was done by someone in the US was actually completely false and was a great scandal somehow, a vast fraud about that just by looking inside. I do not say that superconductivity in superhydride do not exist. What I want to say is that we need to confirm it and to have a reliable way to probe it so that we can compare efficiently measurement done in one team to measurement done by another team, which is definitely not possible with those techniques. This is a kind of expertise that only a few teams in the world can have. And of course, you want experiment to be confirmed, you want more experiment, you want more sample to be explored. So our approach was completely different. Of course, you know that associated to the diamagnetism of a superconductor, it's actually the Meissner effect. And the Meissner effect is the expulsion of a static magnetic field from the interior of a superconductor, with this picture that you've already seen. So what we want to do now is would like to have some compass integrated or close to the sample that could be used to monitor the field distribution very close to the superconductor and observe in real time when we cross the critical temperature that the magnetic field becomes now uniform all over the sample. And for that, of course, you may have imagined what we want to use is to integrate the NV centers and use them as in situ magnetic sensor on the tip, on the anvil tip, to measure this distribution of the magnetic field. And that will allow us to really go in to analyze how the magnetic field interacts with the superconductor, and that avoids all kind of bias that exist that could avoid the main bias on that. So what I want to do now is to show you how we implement this very simple idea. And the very first, we have to create the NV centers. But at that, as I mentioned, we have this remarkable tool developed by Martin Schmidt in our team, where we have now, we can implant the nitrogen atoms, convert them into NV centers. And you have here, on an anvil tip of a diameter of 300 micrometers, just arrays of NV that were produced with a pitch of 10 micrometers. Each NV dot has a diameter of 2 micrometers in this experiment, or just a layer of NV uniform with uniform density that can be used for wide field NV magnetometry, as I showed you before. So we do that, and now what you simply have to do is basically to implement all the tool I discussed with the constraint of a diamond anvil cell. And the first, so basically the idea is very simple. Diamond is transparent. So we can excite the NV layers through one anvil and collect the light emitted by the NV layer through the anvil again by the same microscope objective here. We have to apply the microwave excitation. And for that, we wanted from the very beginning to avoid anything inside the coil, inside close to the sample, and to have a microwave excitation as homogeneous as possible. So I show you in the implementation of wide field magnetometry that we use these simply a coil consisting of 2 turns of copper wire. So we simply do that idea. We'll put on top of the gasket this microwave wire that we do ourselves and hope that it works. When we tried, we didn't work at all. We saw no NV resonance. And then we thought a little bit, and then we found a reason for that. If you put something on top of a metal, it will induce eddy current in the metal. In France, we call that courant de Foucault. Foucault's current, in English, eddy current. And when I was a student, I always thought that that was the current coming from Mr. Eddy. But that's not the reason for that, because okay. So now we change. And basically, we have that. And the magnetic field and that is produced by both the current in the wire and the eddy current in the gasket compensate. And we have B equals 0, as expected in a metal, but also in the interior here, where we have the NV center. And then we had the idea, OK, let's provide that. So we cut now. We prevent the eddy current by making a slit. And actually, we're very proud of that idea, and we found that that was also already invented a few years ago by Ike Silvera in Harvard. Okay, nevertheless, actually, this simple idea worked. We were happy about that, and then we thought a little bit again, and we found that the slit was actually very acting more in a way more subtle than we thought, because somehow the eddy current will be redistributed, and somehow now close to here, you see that they turn the same way as the coil, as the current in the coil. So somehow it's a way to focus the microwave excitation, and that's what we also discovered that this was already found by many people, and people call that a lens, L-E-N-Z, lens. Okay, a way to focus by induced current, a microwave excitation, and that was implemented in microcoil for NMR. Again, many people are clever. Then what we thought after that is, of course, you may say now we have the slit. First, you fill it. You fill it with whatever you can. So it's HBN powder or diamond powder or whatever, and then epoxy glue. But this is not working so well. So either the slip opens, and then that was a complete failure, or the slip closed. It was again a failure. So you have to find a design. So we worked a lot on optimizing the design on the slit, and we found that somehow with this shape we can go up to more than 100 gigapascal with a very stable shape of the slit. And the slit is cut with a femtosecond laser. So we have a femtosecond laser, and we can design the shape of the slit that we want using this system. OK, and then you see here, again, another view of the slit cut in the metallic gasket. What I want now to show you is a recent experiment. So we did that for a long time. No, I forgot something. Oh, yes, I forgot one slide. OK. So let me see if I can add one slide. That's strange. Just I remove it. I was too quick. Yes, this one I should add. It was too quick when I removed the slide. OK, so now we somehow can do NV magnetometry in diamond anvil cell. And in 2019, there was actually 3 papers published back-to-back in Science, where we show both that indeed this technique can be used to measure magnetic properties and at the same time to measure superconductivity. The 3 teams were our team at INS Paris-Saclay, working in collaboration with Paul Loubert's team at CA. The team of Norm Yao in Berkeley at that time, now is a professor in Harvard, together with Raymond Jeanlos, who is a high-pressure expert work that has done really a pioneering experiment in earth science. So using diamond anvil cell, he was able first he was the first to mimic earthquakes. So, and basically, he used, he could put some microphones, somehow, techniques to understand cracks occurring in rocks that were mimicking the occurrence of an earthquake. So he did this work, which was remarkable, and many other work. Paul Loubert did this remarkable experiment recently on metallic hydrogen. And that's the team in the US. And the other team was in Hong Kong, but led by Shen Yang at Chinese University of Hong Kong. Now he's at Hong Kong University of Science and Technology, together with Sui Go, who was also was an expert of quantum materials and was applied for his research a lot of high-pressure techniques. So it's always a combination of people that have knowledge of NV centers plus people having the knowledge of high-pressure techniques. So in our case, for instance, what we did was to investigate a well-known pressure-induced transition occurring on iron. So if you have iron, you know that iron in our conditions can be ferromagnetic, and that's associated to this specific crystallographic structure. But now if you go to higher pressure, even at ambient temperature, you go to this new phase of iron, and in this phase, iron, there is not anymore ferromagnetism. There is no magnetism at all, and the reason is not completely clear, even now. So there's a lot of studies to understand what the reason for that. Nevertheless, we said this is a nice testbed system. So what we do is we have here inside the sample little beads of the iron, and we apply pressure on them. From the bead of the iron, we magnetize them with this technique. And again, with our 4NV orientation, we can really directly see the magnetic field arising from the bead. We can even go to a really quantitative measurement by, again, the same approach as I show you with the permalloy dot. And when we increase now the pressure, the magnetic field produced by the bead will get smaller, 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 and smaller until it disappeared. And if we release the pressure, we see that the magnetic response starts again. There is some hysteresis due to the size of the bead and the fact that it's certainly non-monocrystalline, a single crystal, but we could see that until at one point we do not have points afterwards because we broke the anvil. That sometimes happens. And then another experiment we did, that are results that were obtained in Norm Yao's team on gadolinium. At the same time, we were looking at can we observe the superconductivity through the direct observation of the Meissner effect? And this is our proof of principle experiment. We put in the anvil here a system where we have now a powder of MgB2. MgB2 is a well-known superconductor that has a pressure, and its critical temperature will change with pressure. And what we see is below the critical temperature, we apply a magnetic field like that. And the magnetic field in the z direction will have the same projection on the 4 axes of all 4 families that I have. This is important. So what I see, all 4 families will have the same Z-man splitting. And now I plot the Z-man splitting here as a function of the position. And this map is directly obtained by wide field magnetometry. And what you see here is that on this point here, sorry, let me see, poof. Okay, what you see here, okay, it's the fact that somehow the magnetic field is excluded from the superconductor. So it means that the NV here do not see anymore a magnetic field, or a magnetic field which amplitude has been strongly decreased by the Meissner effect. And this is exactly what we observed here when we looked to the Z-man splitting. The Z-man splitting here is much smaller than the one that we have at the outside of the sample. Okay? So here we have a direct proof that there is expulsion of the magnetic field. And now if we increase the temperature, this expulsion will become weaker and weaker up to a point where we now have a uniform distribution of the magnetic field that's experienced here. And from just measuring the Z-man splitting on top of the sample, we have this curve, this shaped curve, and we can determine from that the critical temperature Tc, and this critical temperature is 30 Kelvin as observed, measured for this compound with other techniques. And that was done at a pressure of 7 gigapascal. Okay, so that's a kind of proof of principle, but now what we want is to go beyond that, is really to analyze what really happens carefully, and especially to detect the magnetic field penetration in the sample. And so for that, we studied, that was the work of Cassandra Daiduz as a PhD student during the 3 past years. And we used a sample, very good sample, that was grown at CA by Dorothée Colson and Anne Forget. So what we have been doing is reproducing the experiment by Paul Shu in the 90s. And of course, the great advantage that those systems are stable at ambient pressure. They do not require, like these superhydride, to be synthesized at high pressure. So we introduce them in the diamond NV cell. So you see here the structure of the compound. This is here the compound of a small flake of these cuprate superconductor. You see here, that's the gasket. And you see here the slit here in the gasket. Okay, the main element that I've seen. And everything is filled with a pressure transmitting medium, which is argon gas. But of course, as soon as you apply some pressure on it, it becomes solid. So now we do the experiment. So this is an image of the flake, which is a little bit, as you can see, which has some homogeneities that you can see here. And we integrate it here, so it's the scheme, and we study it, again, using wide field magnetometry. So you see the different steps, the different elements, as I showed you before. And this is now the PL intensity recorded over the sample. And what we do is apply the same technique as I discussed. So we record at a given temperature, we scan the frequency. We record for each scanning frequency the intensity map recording using the CCD camera. And then we simply change slowly the temperature. And we have all these set of information that we can now reanalyze afterwards. That's a huge amount of data. And it was not clear how to use them at DEST in a very practical way. So I will try to explain how we do that. So this is something which, to seem that strangely, is perhaps the first time that people have really mapped how the critical temperature is distributed in a crystal. We can do the experiment on one point. Like, for instance, choose one point above the superconductor. Let's say, I think it was something like here, if I remember well. And we measure, like before, the evolution of the ZPL, of the magnetic resonance of the NV center for the 4 families with a small magnetic field that is applied of 3 millitesla applied along the z-axis, and the z-axis is also the 1, 0, 0 axis of the diamond field. So what you see is that the magnetic field, we have 2 ways to do the experiment. The first one is called zero field cooling, and the other is field cooling. We'll try to explain the difference later on. In these 2 regimes, we observe the same behavior. You see a sudden a signal that is an ODMR splitting, which is strongly reduced, and at one point, which becomes uniform, the same value outside the crystal. And from this evolution, we can infer the critical temperature here, and we have the same value for the 2 protocols that are used, and I will explain them. And we can do some map of the magnetic field of the TC, because we're using our data, we have this information all over the sample. So we can do the TC map, and we can have the value of the TC. Of course, there are parameters that are outside, values that are obtained outside due to the Meissner effect that creates a distortion of the magnetic field distribution even outside the sample, but this is not relevant data, of course. And we can see now that the temperature, the critical temperature in the sample, above the sample, will change by a few percent regarding what the average value. And all the data analysis is described in this paper. So, what is the difference between field cooling and zero field cooling? The zero field cooling is something where you have your sample, you cool it down much below the critical temperature, and you apply the magnetic field. And you see now, then Zeeman, the Meissner effect occurs, and you see how the Zeeman effect will disappear when you cross the critical temperature. Okay? Now, the field cooling regime is different. You start from non-superconducting state at temperature above the critical temperature. You already applied the magnetic field, and you cool it down. So somehow the system will keep the memory of the magnetic field, and you have it down here, and then with the magnetic field on, now you increase again. So in that case, you see that there are slight differences that have appeared if we compare, for instance, this zone. We see that the 2 regimes do not provide the same information. And why for that? And the reason for that is that actually the magnetic field, if there are inhomogeneities in the sample, the magnetic field that is applied during the system, during the cool down, can penetrate already into the sample and somehow create little zone where there won't be the Meissner effect. And this is what you observe here. So this is, for instance, can be due to trapping zone where the magnetic flux gets trapped. And so you can confirm that by a 3rd experiment, which is called the flux trapping experiment. And this is perhaps what I think the very beautiful experiment, in the term that now what we do is that we apply a magnetic field, okay, when we cool down the system, like before, but instead of now heating the sample with still the magnetic field, we remove the magnetic field. Now we have launched somehow some superconducting current inside the sample, and those superconducting currents can survive for almost whenever. And that is an experiment that says that this superconducting current launched in a superconductor can stay there for years. So we try to do, now this is what we have done. Somehow we remove it and we try to see what happens. And what you see is that the superconducting currents create some areas just above the sample that emits some magnetic flux, that create the magnetic flux. And somehow this is due to some current here circulating that exist somehow, that were responsible for the difference between the field cooling and the zero field cooling image, that were due to magnetic flux really trapped inside the signal. So that's another proof of existence of superconductivity. at least for for type 2 superconductors. And now if we increase the temperature, then the system will go to this superconducting current will decrease progressively, and it will disappear. And from that, from this evolution with temperature, we can also determine the critical temperature in good agreement with the value we obtained before. Okay, so, and this correlates well. The zone where the magnetic flux is trapped correlates well with the area where we could really see a strong difference between the two images we obtained, both with zero field cooling and field cooling technique. So now we have all this set of methods which we believe are very powerful and well, and with efficiency has been really proved by us, by other persons. There is a lot of work now done in China applying our techniques, applying this technique of NV magnetometry for high pressure experiments. But the question I would like now to address is there a pressure limit? And that was an important point. We want to apply those techniques to investigate, for instance, the superconductivity of superhydride that exists at pressure above 100 gigapascal. And let's see what happens. So this is experiment which was done again with the same sample, the same compound, at 1 gigapascal, and now at 30 gigapascal. You observe that the contrast of the ODMR signal is strongly reduced, up to a point where basically, if we increase a little bit more the pressure, we cannot see anything. So somehow the signal, the NV signal deteriorates with pressure. And that was, people thought that this would be a kind of practical limit for NV magnetometry, somehow around 30 to 40 gigapascal. So the question is, why does the NV Meissner signal deteriorate at high pressure? And can we maintain the signal at pressure above this practical limit? And if we look more carefully at what happened to the NV in the tip, we have to realize that the NV are in a stressed environment. And NV centers are sensitive to many parameters through the dependence of the lattice, but they are also very sensitive to the strain or the stress that is applied around us, of the matrix in which they are located. So, of course, when you build your cell, you have to do very accurate adjustments so that the two anvils are perfectly parallel to each other. If there is any mismatch of angle, when we squeeze them, immediately it breaks. So we take great care in the adjustment that the two anvil tips are really parallel. And this is observed, for instance, in this observation here. You see that there is there's a uniform light going here when we look through the anvil. But when we now apply the pressure on the tip, you can imagine that there are huge forces that concentrate on the tip, together also with the huge forces that are exerted laterally by the tip. So what happens is that the tip becomes, the anvil tip has now a curvature. Okay? There's a cupping effect on the tip. And this cupping effect, due to the competition between compression on one side and surface tension on the other side, leads to this shape of specific shape that you can really observe. This is the distortion here, the fringes here, tells you that you have indeed these interference, this shape of the diamond anvil. So since we have now the NV centers at the really above the tip, what will happen at the surface of the tip, what's going to happen is that those will have a strong stress that is applied not on their axis. So somehow we will have the NV center that's in an environment which is non-hydrostatic. That's what we think. So if we do that, we can model this effect by applying a stress tensor at the anvil tip, which is quite simple. We say that in the Z direction, there is a pressure that is applied. And on the transverse direction, due to the cupping, we have it is reduced by a parameter alpha. due to the surface tension. And alpha should be below 1. So from using that, we now integrate that into the Hamiltonian. And once we have that, we can measure now the Z-man dependence as a function of this model. And we clearly see positions of the resonances that's in very good agreement with this model and alpha parameter, which is around 0.6. And you see two effects. You see first this effect, the mean frequency is going up. Okay? And this can be understood very simply. I have the two electrons of the NV. When I apply pressure, they get closer and closer and closer. So I strengthen the magnetic dipole-dipole interaction between the two electrons, which leads to an increase of the D parameter. Okay? But at the same time, the non-hydrostatic stress, transverse component of the stress, will mix now the quantum state plus and minus somehow, will mix the state of the basis ms equals 0, plus 1, and minus 1. And this will somehow induce this shape dependent. And also, we believe, also we do not have a model for that up to now. We believe that this will also induce the decrease of the ODMR contrast due to this strong mixing effect. So somehow, but this we don't know. We would have somehow to reproduce all what we know, and especially the intersystem crossing and the metastable singlet state. But this, unfortunately, we were not able yet to do it. We don't know how these non-hydrostatic pressure affect both the singlet state and the intersystem crossing rate. So we left that aside, and we try now, we say, okay, the problem is a non-hydrostatic stress. If we now are in hydrostatic condition, we preserve the intrinsic symmetry of the C3V, C3V symmetry of the defect. The MS0 plus minus 1 will remain the good basis of the system, so we could expect that the ODMR signal will be kept for even at very high pressure. But can we realize that? And our idea was just to mill with a fib or femtosecond laser a pillar on the anvil tip. So somehow that will decouple the pillar from the compression from the cupping effect on the anvil tip. That was the bare idea. So this is a pillar. It's a stiff pillar. It's wider, a few micrometers, and just a thickness of 1 to 2 micrometers, rather stiff, but enough, we thought, and we did some calculation about that. Also, it's quite difficult, but nevertheless, we convinced ourselves that geometry could be efficient for doing that. And the first check is to look at the Raman signal of the diamond. The Raman signal is already a good signature, whether or not to get an insight of the stress environment. So if we look outside the sample, we have this typical signal, and that typical signal can be explained by non-hydrostatic conditions. If we now look exactly on the pillar, we see a new peak that arises, and this new peak with a higher Stokes shift, a Raman shift, is actually evidence that there is a higher pressure somehow exerted here compared to here, on the red dot compared to the blue dot. And if we now look to the evolution of this small peak on top of the pillar as a function of pressure, it follows very well the dependence that was found in hydrostatic condition for the diamond Raman shift. So somehow this is the first evidence that this is an evidence that indeed our pillar technique provides us a method to retrieve hydrostatic condition. So now let's look to what happened to the NV signal. And you see that we keep the Z-man shape. The Z-man dependence is kept now. We do not have anymore the mixing of the state that says to this great splitting even at non-zero field. But there is only now a shift of the G line associated to the dependence of D parameter with pressure. So two electrons simply getting closer. But nevertheless, the C3V symmetry is maintained, and we keep the ODMR contrast. It decreases on this branch, but the decrease is simply due to the fact that our microwave excitation was not efficient above 4 gigahertz, and that was somehow a practical limit, but now we've been able to purchase new equipment and to work with more to get contrast increase at those pressure range. So somehow, and the fit give us a value which is close to unity, saying indeed that we are close to hydrostatic conditions. So somehow, we can now have a method to maintain magnetic sensing behavior unchanged up to 103 gigapascal. So it's no longer a limit if we want to explore the superconductivity of superhydride. And this is now what we're trying to do. It was confirmed in microdiamonds by putting microdiamonds inside the sample with the signal that was observed at that pressure, but perhaps not as convincing as the one we had. But nevertheless, was also an independent proof. And there was another approach that was complementary to us that was done by Norm Yao and also people in China that use now 111 NVIL. And those 111 NVIL, you have one NV family in which you apply the pressure exactly on their axis. So for that family, it's really great because everything is perfect. You keep their symmetry by construction somehow. So it's again another proof that it's indeed the C3V symmetry that matters in everything. And Norm has applied that for a very nice experiment which shows some kind of first evidence that superconductivity can be observed in superhydride using the NV technique approach. So that's very interesting. And at the same time, Jiangfeng Du in Hefei, Chinese Academy of Science, reproduced the same idea, implemented the same idea, but now done, and the paper has been published in Nature Communications, I should put it, that was on some other magnetic materials that have a phase pressure-induced transition above 100 gigapascal. Okay, so we can compare, for instance, benchmark our technique to SQUID. And of course, it's rather difficult to always say I'm better than another technique. But I would like to highlight two main differences. The first one is we're able to work in the same range. And we do not need specific cell. We have a sensitivity that we believe is higher. We have no background. This is some important advantage. But more than that, what we can do is really map the critical temperature. So we can deal with inhomogeneous sample. That's something quite important. And most of as soon as you apply pressure, you can imagine that there can be inhomogeneities created in the materials. Or even if you get the materials from a chemist, that will be certainly non-perfectly homogeneous. It will take years to improve the quality of the materials. So, and to put all the effort on the development. At the same time, the NV magnetometry system that I show you, especially the wide field system, is so simple that somehow we can build a portable apparatus and take it and bring it, for instance, on a synchrotron beamline. And in this experiment that we published a few years ago, we did that. So we observed the alpha to epsilon pressure-induced transition of iron on a synchrotron beamline. So we could do at the same time the measurement by X-ray diffraction of the evolution of the crystal from the alpha structure to the epsilon structure and measure simultaneously the evolution of the magnetic response. And I think this is very important because as soon as also you get some materials, you want to analyze the structure. And now with 4th generation synchrotrons, you achieve resolution in X-ray diffraction pattern at about with micrometer resolution. You can really determine the structure of a sample with this micrometer resolution. And somehow having a tool that measures the magnetic response with the same spatial resolution is something that will be very complementary for all these measurements. Okay, we can apply the same technique to investigate how pressure acts on other defects of diamond. So for instance, silicon vacancy, germanium vacancy. So this is crystals, nanocrystals that embed these defects. You integrate them and you observe and you try to observe, for instance, how their spectrum will change with pressure. This is a very preliminary experiment. But remarkably, our data fit very well with ab initio calculation that were done by Adam Gali and Lukas Razinokovas teams in Budapest and in Lithuania. And we observed that, for instance, there is a very good agreement between the evolution of the ZPN line as a function of pressure up to almost 200 gigapascal. So this tells you that indeed we can really play now with a lot of parameters and understand, for instance, the structure of the effects using pressure to confirm, using ab initio calculation, really the structure that is observed. Okay, so this is just an overview of what we're doing, and we're building, and we hope that in the future many results will come from applying NV magnetometry to the specific context of high pressure measurement. And this is just to show you the team involved in all that during the past years. So my colleague Martin Schmidt, with whom we worked really for a long time now, and we build the NV signal, the implantation machine together with also Margarita Lezik. Margarita Lezik was a PhD and postdoc in the team and left a few years ago, and she's now in charge of a team in a industrial research lab. Marie-Pierre Adam, who is a research engineer in our team, and we do a lot of development and experiment at the moment. And we have two setups. I hope to show you them tomorrow. One here with Cassandra and Claire, Cassandra Daidous and Claire Roussy. It's you have here a small cryostar. You don't see it very well. And here, the NV microscope head on which we can do very easily NV wide field or confocal microscopy. And this is another system. Grégoire Le Carrière de Beauvais, a PhD student here with Kin On-O, was a postdoc for 1 year and a half and is now in the US, coming from Hong Kong. And we have a system here. So it's a cryogenic system from Attocube that can go down to 2 Kelvin. And at the same time here, we have superconducting magnets. We can apply 0.5 Tesla in every direction we want. And Grégoire was able to build, all the optical setup and microwave delivery that can now be used on this system to test superconductivity and other properties of materials at both low pressure and under high magnetic field using NV technique. And that's where somehow all my funding comes from the team. An ERC grant. ERC is a European Research Commission grant. And EUF, that's something in France where basically you are free of teaching for many times to really concentrate of your research. ANR is our funding agency, a national French funding agency. And this is something that provided us a support for a lot of purchase of materials, especially to settle the high pressure center and all the instrumentation that is required for the assembly and technology for the NV for the high pressure diamond cell techniques. And Quantip, it's our federative center in Ile-de-France region around Paris that provides support to the development of science and quantum technology. Thank you for your attention, and we will have this afternoon the lab demo.
So there is time for this session.
And if you have questions, do not hesitate. Okay.